Hello everyone, in this video we will be taking a look at 50 questions which are very important for your last minute IIT preparation, because you can expect questions of these type in your exam. And remember, since you've been given 1 hour to solve 15 questions in physics, if you can solve these 50 questions as you follow the video in approximately 2.5 to 3 hours, then you will be in a very good position and you will comfortably be able to solve 15 questions and have enough time left over so that you can check and verify your own answers as well as spend a little extra time in the other subjects as well. So let's get on with it. The first question says that we have a particle moving in the xy plane which full velocity is given with respect to time as 8t minus 2, and the y component of velocity is constant as 2. And we've also been given that at time t equal to 2 seconds, the particle was at x equal to 14 and y equal to 4. Now there are two ways to solve this question. First way, you will write y component of velocity as dy by dt and place it to 2, and you can write y equal to 2t from here by integrating simply. Then you can write the final velocity or the full velocity as the hypotenuse sort of x and y components of velocity, and then write both of them as dx by dt as the x component and dy by dt as the y component, which we already know to be equal to 2. Then you can integrate these both expressions, eliminate t from them and get an equation in x and y. But this is not what you will do in the exam at all, because this is a very long method. It involves very lengthy calculation and it is very easy to make a small mistake somewhere in between and the entire solution is just wasted. Instead, since we have been given 4 options and there is an equation in every option, we can just check which equations satisfy x equal to 14 and y equal to 4. And since only one option is correct, only one should satisfy and that will be your answer. Let's see. At y equal to 4, let's write y equal to 4 over here, and y square will be equal to 16. Similarly, y cube will be equal to 64. Let us just check the first option in this case. First option says that x equal to x cube minus y square plus 2. Y cube is 64 minus y square is 16 plus 2. 64 plus 2 we get 66 minus 16 we get 50, which is not equal to 14. So option A is not it. Let us check option B now. Y square, that is 16, minus of y, that is 4 plus 2. 16 plus 2 we get 18, minus 4 we get 14. Yes, this satisfies. Hence, your answer will be option B. Don't unnecessarily waste your time when there is a much quicker and much easier way of utilizing every bit of information given to you. Let's take a look at the next question. In this, we have given that a tiger charges towards a hunter with a constant speed, and hunter fires an arrow at 30 degrees to horizontal when the tiger is 100 meters away. Now let's assume the tiger is a spherical object t. It is moving with a constant speed of 15, we know, and a hunter will now fire an arrow 30 degrees with respect to the ground, let's say with some initial speed u, which we need to calculate. Now again, there are two ways of doing this. You can either assume that the hunter will have enough judgment that he will fire the arrow such that it will land at the exact spot that the tiger will be when the arrow hits the ground. Otherwise, you can assume the tiger to be at rest and then calculate the relative velocity of the arrow moving towards it. In that case, the arrow will have to cover 100 meters, but its speed will now be different. Let's see how to do it. Let us first resolve the initial velocity into its horizontal and vertical components. The horizontal component will of course be u cos theta. Since theta is 30 degrees, it will be root 3 u upon 2. This will be the horizontal component of the initial velocity. And of course, vertical component will be u sine theta, u sine 30 degrees, which is simply half of u. So this is how we can split the initial velocity into its horizontal and vertical components. Now, we know that time of flight of the arrow has nothing to do with the horizontal component of initial speed nor the horizontal acceleration. Time of flight only is dependent on the vertical component, and we can write this time of flight as 2u sine theta by g, that is twice the vertical component upon g. We know sine theta is half, that can cancel with 2, and the time of flight thus comes out to be u by g. We can write g equal to 10. Now we need the horizontal component of the arrow. Again, with respect to the tiger, we can write it as vx as the horizontal speed. Horizontal speed of arrow initially is u cos theta, which we know it to be root 3 by 2 into u. And since tiger is moving towards the arrow at a constant speed, we can add 15 meters per second, that is the speed of the tiger itself, to the horizontal component. This will be the horizontal speed of arrow, and now we need that in a time equal to time of flight of the arrow should cover 100 meters with this relative speed. So we can just write r, that is the range required, should be equal to horizontal component of speed into time of flight, that is horizontal component of speed. We can just multiply with u by 10. So root 3 into u square over 20 is the first term, and 15u by 10 is the second term, and this should be equal to 100 meters. Only then will the arrow hit the tiger once it lands on the ground. We have a u square, we have u, so this will obviously be a quadratic equation. In order to get a common denominator, we can multiply second term by 2, so we will get root 3 u square plus 30 times u. 20 into 100 gives us 2000, so minus 2000 equal to 0 is our quadratic equation in 2. The positive root of this equation will give us the required initial speed. Let us then write down the quadratic formula. We have u, again we need the positive root, so minus of b, that is minus 30, plus square root of b square minus 4ac, that is, sorry, this is 2000, b square is 900, plus 4 into 2000 is 8000 into root 3 upon 2 root 3 completes the quadratic formula. And if you simply calculate this using the calculator provided to you, you should get, let me quickly calculate it using my own calculator. Yeah, approximately 26.1 meter per second is the required initial value of the velocity that we're getting. Hence, option D will match over here. Let's take a look at the next question. Here is given the fact that 10 blocks, each having mass 2 kgs, is let go from a table, that is, they start sliding down, and we need to calculate tension in the 7th and 8th block when the 6th block just slides off. So let us draw a 6th block sliding off, 7th block, 8th block, 9th block, and 10th block will be connected as such, and all of the other 6 blocks will be hanging from the table. These are 6 blocks, and each of them will have the same acceleration. Since all the blocks are connected by ideal strings, every block in the system should have the same acceleration, whether horizontal or vertical. But the driving force of the system will only be provided by the weight of the blocks that are hanging. So driving force of the system will be 6 times mg, that is the weight of the 6 hanging blocks. This should be equal to the total mass into acceleration of the system, which is 10 into ma. M and m will get cancelled, and since we have the value of g, we can take to be 10. So acceleration of the entire system, we get 6 meter per second square. Now we need the tension in between the ropes of 7th and 8th block and 6th and 7th block. Let's say that 6th and 7th block are connected by a string that has tension T dash and the required tension T of the 7th and 8th block. If we draw the free body diagram of the 7th block, we know it is moving with an acceleration of a towards the left, and it has a force T dash towards the left and a force T towards the right. Now, if we draw the free body diagram of the combined system of 6 mass hanging downwards, then the combined mass is 6m, its own weight 6 mg is acting downwards, and the tension between ropes T dash is acting upwards, such that the acceleration of this entire block system should also be equal to A in the downwards direction. Now we can balance the forces. First at the 6 blocks, and we get the value of T dash from here. If we can just balance the forces, then 6 mg minus T dash should be equal to 6 into ma. 6 mg minus T dash should be equal to 6 times ma. We can get the value of T dash from here as T dash is equal to 6 times mg minus 6 times ma. Since mass of each block is 2, then 6 into mg will be 120 minus 6 into ma will be 72. So we get the value of T dash to be 48 newtons. But we need to find the value of T, that is the other tension. So we can now balance forces on the 7th block. Driving force is T dash, acceleration is A. So m into A should be equal to T dash minus of the tension required T. We can now write the value of T similarly as T dash minus ma. T dash is 48 newtons and ma is 2 into 6, that is 12 newtons. So we get the value of T as 36 newtons, which is matching with option B. Again, simple laws of motion you can apply on each and every single block and you will easily get the answer. Now in this next question, we have a block M1 which is colliding with a block M2 completely inelastically. That means after collision, let's say before collision the mass M1 was moving with some speed u and M2 was at rest that we've been given. After collision, we know since it's a completely inelastic collision, the two masses will stick together and move with some common speed, let's say v. If we want to find the value of v, all you have to do is simply conserve the momentum. Initial momentum was m into u, final momentum will be m1 into u, m1 plus m2 into v will be the final momentum. Now we can find the value of v as m1 into u upon m1 plus m2. This is the value of the final velocity of the blocks that we are getting. Now we need the ratio of the kinetic energy transferred to mass m2, which is basically kinetic energy of m2 after the collision. So value of k will be half into m2 into v square, that is half into m1 m2 u square upon m1 plus m2 the whole square, and initial kinetic energy k1 was again simply half into m1 into u square. Now the ratio k upon k1 ratio will be given by half into m1 m2 u square upon m1 plus m2 the whole square upon half mu square, which we can multiply as 2 upon m1 into u square. 2 and 2 will get cancelled, m1 will get cancelled, u square and u square will get cancelled, and our ratio k upon k1 will simply come out to be m1 into u upon m1 plus m2 the whole square. There should be one more m1 over here. Oh yeah, there was an m1 square over here, so only the square term will get cancelled, and our ratio will be m1 into m2 upon m1 plus m2 the whole square. Now if you want to bring the m1 m2 numerator term also inside this square, all we have to do is wrap a square root around it, because we know m1 into m2 is simply square of under root m1 into m2. So in order to bring m1 m2 inside the square, all you have to do is paste a radical sign, and this becomes our ratio of kinetic energies. but all the options are in terms of the ratio m2 upon m1. So let R be the ratio m2 over m1, and now we have to represent this k upon k1 ratio in terms of R. For that, it will be better if we take m1 m2 in the denominator and m1 plus m2 in the numerator, so that we can split it into terms individually. So the ratio we can now split as 1 upon m1 plus m2 upon square root of m1 into m2, the whole square. Now if we split the denominator over here, then 1 upon m1 upon root m1 plus m2, sorry, m1 into m2, m1 will get cancelled and we'll have a root m1 in the numerator. So we have under root of m1 upon m2 plus m2 upon root m1 upon m2. Again, we'll have m2 in the numerator upon m1, and the whole square completes. So we are basically getting the ratio of kinetic energies k upon k1 as R was m2 by m1, so 1 upon root R plus root R whole raised to minus 2, since we are taking this in the denominator. So this is the ratio required in terms of m2 upon m1. Now let us check the options. It is clearly not equal for all values of R, because if R was something like 4, then our ratio would be 1 upon 2 plus 2, that is 2 by 5, square root 1 upon 0.5, which is obviously not equal. If R was 14, we would get 1 upon 4 plus 4, that is 4.25, square root some 2 point something would get. So obviously it is not constant for all values of R. If this was independent of R, then we could say yes, it is constant for all values of R. But since it is very, very dependent on R, it is not constant. Now, next we have to check when this will attain a maximum value. Now, the usual way to check this is by differentiating this with respect to R. This final ratio, if we differentiate d by dr, put it to 0, we can find the value of R at which it will be maximum or minimum. But remember, whenever you have a condition of maxima or minima in physics, that means there should be some symmetry in the system. It's a very, very important concept applicable for literally all of physics. Whenever there is a maxima or minima condition, there will always be some symmetry in your system. Now, the only way in which this expression can be symmetric is if R equal to 1. So 1 upon root R will also be equal to 1, and root R will also be equal to 1, and that will be the value where we will get the maximum ratio, where ratio is 1. Remember, very, very important, maxima or minima means there should be some symmetry in the system. This will save you lot of valuable time while solving questions. Remember this. And of course, since this is a maximum value at m equal to 1, m2 equal to 1, then for all other values, the ratio will decrease. So our option C is also correct. And if we substitute R equal to 1 in the expression, then 1 plus 1, that is 2, minus 2, so 1 upon 4. So we also get the maximum value as 1 upon 4. This is the old nest question. At that time, they used to have multiple option correct. But again, remember this one key fact, that whenever you have maxima or a minima condition, there should be a symmetry in your question, or at least in your expression. This will save you a lot of time. Now this next question says that we have a 3-block system such that initially a block of mass m was moving towards the right, and it collides with a mass of 4m. One collision will happen over here, and if the block moves in the other way, then it will collide with the second block and another collision will take place. But we know that in order for further collisions to happen, the condition for collisions is that if there are two blocks chasing one another, if this block is chasing with speed u1 and another block is running away with speed u2, collision will only happen if u1 is greater than u2. Otherwise, there will be no collision. Block m2 will keep moving and m1 will not be able to catch up. So we have to check the condition of collisions each time. Now, since 4m was at rest initially, of course, the first collision will happen. Let us solve the first collision. After collision, let's say the block of mass m starts moving towards the left with speed v1, and the block of mass 4m starts moving towards the right with speed v2. Now, if we conserve the momentum in the left direction, we get m1 into u, which was the initial speed, to be equal to 4m into v2 minus v1 minus mv1, sorry. We can cancel m from all these sides just for convenience. And if we substitute the condition for an elastic collision, we know velocity of separation should be equal to velocity of approach. Since 4m was at rest initially, velocity of approach is nothing but u, and velocity of separation, since they both are moving in the opposite directions, both of their velocities will get added up. v2 plus v1 will be the velocity of separation. If we add these two equations, we will get twice of u is equal to 4 plus 1, 5 times v2. From here, we can get the value of v2 as twice of u over 5. So, after the first collision, 4m block will start moving with a speed 2u by 5 towards the right. And since v1 plus v2 should add up to u according to our second equation, we will get the value of v1 also to be u minus 2u by 5, that is 3 times u by 5 will be the initial velocity for the other collision. Let's solve for the second collision now. In the second collision, initially mass m is moving towards the left with speed 3u by 5, that we now know, and 4m is at rest. Let's say after collision, the block of mass 4m starts moving towards the left with speed v2 dash, and the mass m starts moving towards the right with speed v1 dash. Now, conserving momentum, once again we get initial speed 3m into 3u by 5 should be equal to 4m into v2 dash minus of m into v1 dash. Once again, m will get cancelled from all the sides, and perfectly elastic collision, so velocity of approach 3u by 5 should be equal to velocity of separation, that is v2 plus v1. Once again, adding both of these equations, simply we get the value of u2, 6u over 5 should be equal to again 5 v2 dash, and hence the value of v2 dash will be equal to 6u over 25. So, after second collision, the 4m block will start moving with velocity of 6u by 25, and for the body m, we can again use v1 equal to v2 dash, v1 plus v2 dash equal to 3u by 5. So, the value of v1 dash will be equal to 3u by 5, that is the initial speed, minus of 6u by 25. To make the denominator common, we'll have to multiply this side with 5, 15u minus 6u, that is 9u upon 25 will be the velocity with which the block of mass m will start moving after the second collision. And since the first block was moving with 2u by 5, that is 10u by 25 is faster than the mass m after second collision, so the block will not be able to catch up with the block ahead, and there will be no further collisions after second one. So there will be total of 2 collisions in the system. Let's take a look at the next one. Here we have a block of mass m sliding down the ramp and getting stuck to a rod of mass m and length l, and the system then rises by an angle theta, which we have to find. Now we know length of the rod is l. Initially the length was l, so if we draw a horizontal at the final position of the block, then we know that this component is equal to l times cos theta. Hence the change in height will be l minus l cos theta. If we take l common, then 1 minus cos theta is the change in height of the block of mass m. Similarly, center of mass of the rod will also rise by l by 2 into 1 minus cos theta. Now, if it was a perfectly elastic collision, no loss of energy, so we could have simply equated initial potential energy to the final potential energy, and in one step we had the value of theta. But since there is some energy loss which we don't know what, we have to equate the kinetic energy after the collision to the gain in potential energy. But first we need the kinetic energy after collision, for which we need the velocity with which the rod will be rotating after collision. We can do this by conserving angular momentum. We know that after falling a ramp of height h, the block will gain a speed of under root 2g h. So initially the angular momentum about the point O of the block of mass m will be m into v into r, that is m into under root 2g h into length of the rod, which is the radius. And finally the moment of inertia of the rod is ml square by 3 about its end into omega, plus moment of inertia of the small block will be mr square, that is ml square into omega. So omega is the final rotational velocity of the rod as well as the block are about the axis O. Now in order to make the denominator constant here also, we can multiply 3 with m and send it to the LHS as well. The value of omega will then be 3m under root L, and L will get cancelled from here, 2gh upon mass m plus 3 times m, capital M plus 3 times the small m into L. So this will be the angular velocity with which the rod as well as the block will be moving after collision. I hope I haven't made any mistakes here. Right, no mistakes made. Now we can see a pattern emerging, capital M plus 3 times small m. We have capital M plus 3 times small m in the options C and D as well. So we know we are going the right direction. Option A and B have all been eliminated. And now if we calculate the kinetic energy of the system after collision, then it will be just the rotational kinetic energy half into moment of inertia of the rod is m L square by 3 into omega square. We can simply square this, 9m square into 2gh upon capital M plus 3 times small m whole square into L square, which will cancel the L square in the numerator, and we will add the moment of inertia of the mass into omega square, 9m square 2gh upon capital M plus small 3 times small m the whole square into L square. Again L square will get cancelled. Now in order to make the denominator common again, we can multiply this 3 with the mass 3m and take the rest of the terms all constant. See, the two terms only differ by the capital M by 3 term over here. There's a capital M by 3 term on the left term and a small m on the right hand term. So if we multiply just this 3 over here, then we can take the rest to be common. Taking the rest common, we have 9m square into 2gh upon, these are 6 into capital M plus small m the whole square, and this is multiplied with the mass capital M plus 3 times mass small m, which will simply get cancelled with 1 square. So we have this as the kinetic energy term. Now if we just cancel 1 3 from here and leave it at 6, then we will get this term as 6 into m square h into g upon, we had cancelled 3, right? So twice of capital M plus 3 times small m will remain. Now we can see 6m square h. 6m square h is another pattern that is repeating over here. Let us now equate this to the gain in potential energy of the system, which is simply mgh of all the objects. For the rod, the center of mass of the rod rises with L by 2, 1 minus cos theta. So that will be the gain in potential energy. and the gain potential energy of the mass is m into g into h, that is L into 1 minus cos theta. This will give us the exact value of theta. Now we have most of the pattern same as the options C and D. The only way in which C and D are different is there is a radical sign in the option D and no radical sign in the option C. Now we can see that in option C and D both, there would be an expression of this sort. We will take something common with 1 minus cos theta, and this would be equal to some big term over here, and we can rearrange now this equation, take cos theta on the RHS and this big term on the LHS, and we would get an answer of the form 1 minus some big bracket should be equal to cos theta, and we can then write theta equal to cos inverse of the entire LHS term. But if we had 1 minus cos square theta in our expression, then there would be a square root sign in the cos inverse function. And option D would be correct in that case. But since we only have 1 minus cos theta, we need not even solve this question further. There is no way we are getting cos inverse function over here. So C has to be the answer to this question. Again, you can see that you don't always need to complete the entire calculation. Sometimes, judging from the options, the answer becomes apparent to you. Next question now. We have the fact that from point A, a ball is projected from an inclined plane. The inclined plane was an angle of, let's say, phi with the horizontal, and we are projecting a ball at an angle of theta with the inclined plane and with some speed, let's say u, and it has been given that after the second bounce the ball rises perpendicular to the plane. That is, after the second bounce the velocity of the ball parallel to the inclined plane becomes equal to 0. This is the condition that we need to check after the second bounce. And let the coefficient of resolution with the inclined plane be E. We know that the acceleration due to gravity is g in the vertically downward direction. But since we need to check the parallel component of velocity, it will be better if we rotate our axis. Let's rotate our axis system so that our x-axis, our new x-axis, will be in the parallel direction to the inclined plane. Let this be our new axis, which we can see is parallel to the inclined plane. Let me draw a little better. This new axis is parallel to the inclined plane, and our y-axis will now be perpendicular to it. We know that it makes an angle of phi with the x-axis, and perpendicular to it will be our new y-axis, y dash. Now we know acceleration due to gravity is in the vertically downwards direction. Now if we make this axis system such that x dash is horizontal and y dash is vertical, we can see why am I not able to rotate this? Okay, fine. Let me just draw it individually. X dash axis will be in the horizontal direction and y dash axis will be perpendicular to it, and the actual horizontal x axis, our old x axis, will make an angle of phi with our new x axis, and acceleration due to gravity will also be perpendicular to our old x axis. Hence it will have some component in the y dash direction and some component in the x dash direction also. The y dash component will be given by g cos phi because it will now make an angle of phi with the y axis, and the horizontal component will be given by g sin phi because it makes an angle 90 minus phi with the x dash axis. This is how we can split the acceleration due to gravity in terms of our new axis. Now we know that in order for the parallel component of velocity to be equal to 0, after some time we can write the parallel component of velocity Vx dash equal to initial component in the x dash direction was simply u cos theta, and acceleration in the horizontal direction is g sine theta g sine phi into time t. This will give us the parallel component of velocity at any time t. Now, in order to check the value at the second bounce, we need the time elapsed until the ball bounces 2 times. We know that time of flight of a projectile, especially like this, is only dependent on the vertical component of velocity as well as the acceleration. So, time of flight for the first bounce will simply be 2 into u into sine theta upon g into cos phi, because the vertical component of acceleration is g cos phi. This will be time taken for the first bounce. After first bounce, it will rise with a velocity e times the velocity perpendicular to ground. So the new time of flight for the second bounce can now be written as 2 into eu sine theta upon g cos phi. This will be the total time of flight until the ball bounces 2 times, and after this much time, the parallel component Vx dash should exactly be 0. Let us now substitute small t as this time of flight, and then it should balance with the initial horizontal velocity u cos theta. So g sine phi into t will now capital D be equal to, just multiply g sine theta with both the expressions, and we can take 2 into u sine theta common. 2 into u sine theta into g sine phi over g cos phi. G will get cancelled with g, and remaining 2u sine theta cos theta upon sine phi gives us tan theta. So we get, tan phi. We get tan phi from this side, and we can take this common. 2u into u square, no, only u, 2u into sine theta into tan phi we had obtained should get balanced by u into cos theta. So u and u will get cancelled, and oh sorry, I forgot to take it common. 1 plus e will come out in the brackets by taking 2u sine theta upon g cos phi common, and this should get balanced with u into cos theta. U will get cancelled with u on the LHS, and 1 plus e, we can take all of these terms in the denominator. So we get 1 plus e to be equal to half. This 2 will come in the denominator. Tan phi will become cot phi. Cos theta upon sin theta will be cot theta and cot phi. So E becomes simply this minus 1. Option D matches in this case. Again, this is a calculation heavy question. This is also a very, very logically heavy question. But as long as you can see that as the ball rises perpendicular to the inclined plane, the parallel component of velocity will go to 0. You will immediately be able to see that, okay, if I rotate the axis such that x dash, the new axis, is along the incline, then I can just simply take the x dash component of velocity to be equal to 0 for this condition, and hence you will exactly get the equation coefficient of restitution also. Next question, we have a rod of length L at room temperature such that if we raise temperature by delta T as well as apply some compressive force, then the change in length in it should be 0. We need to relate the Young's modulus to it now. Now we know that by heating a rod by delta T, the length of the rod changes as delta L is equal to length into coefficient into delta T. Now, if we use the expression for Young's modulus, we have y is equal to force into length upon cross-section area into change in length. So, for this delta L amount of change in length, we require a force such that delta L is equal to force into length upon area into Young's modulus y. Now, all we need to do is ensure that this change in length that is obtained by application of this force is equal to the change in length that is obtained by heating the rod. So we can simply equate F into L upon cross section area into change in into Y, not change in L, Young's modulus Y. Length and length will get cancelled and we will get the value of Young's modulus Y as F upon A into alpha into change in temperature. That's it. F upon alpha into D. Option matches in this case. Again, questions from properties of matter, fluid mechanics are very easy. You have to only remember at max 1 or 2 concepts and you will be able to solve them pretty quickly. Now in this question, we have the fact that a pendulum made of a wire. We are not making pendulum out of a string but of wire now. We know that adding a mass m to the bob should not change the time period of an ideal pendulum. But this is not an ideal pendulum. This is made up of a wire and we know that if we add an additional weight to a wire which is clamped, let's say this wire has Young's modulus Y, L and area A. If we add some additional weight, capital M into G, it increases the length of the wire also, and we know the amount of length increased FL upon AY. So the change in length is the applied additional weight, that is mg, into initial length of the wire upon cross section area into the Young's modulus of the wire itself. So the new length of the wire will be L plus this much change in the length also. And we also know that for a pendulum, the time period is equal to 2 pi square root of length of wire upon acceleration due to gravity. So we can say that time period is proportional to square root of length of the wire. So if we need the ratio of time period after adding a mass m to the initial time period, we can simply write the ratio as Tm upon T to be equal to the ratio of their lengths L plus delta L, which we can now write as L plus mg upon Ay. We can take L common and 1 plus mg upon Ay will give us the new length of the wire, and dividing by L we can get the ratio Tm upon T. Now if we square this term so that we can remove the radical sign from the LHS, we will get Tm over T square should be equal to 1 plus mg upon A into Y. Now since we want 1 upon Y, we can take 1 to the LHS. So we get T at m upon initial T whole square minus 1 should be equal to mg upon Ay. But we want the value 1 upon Y, so we can multiply it further by A upon mg by taking them to the LHS, and this will get the value 1 upon Y. Again, option D is matching in this case. As I said, all you have to remember is some basic concept of elasticity, and just by applying logically whatever is asked in the question, you will easily be able to get the answer with just a few steps of quick calculations. Next question, we have that the long metallic wire is tied to a ceiling and the other end is tied to some massless string. Let us draw a diagram quickly. This is a ceiling, there is a wire of length L, area A and Young's modulus Y, and it is tied to some spring of spring constant K, which is then tied to a block of mass M. Now if we displace this block, there will be some displacement x1 in the spring and some displacement x1 in the wire, some strain x1 in the wire will be produced. We can calculate the time period separately and then compare them, but again that will be a very long and windy way to do it. Mistakes also are possible, so we can do smart work over here. We can assume that there is no spring in our system. Let's say there was only wire. So for only wire in our system, for only wire without the spring, we can consider that any force applied on it will cause some strain of x. So we can write the Young's modulus as F into L upon A into delta L, which is X we can write. So from here we can write the value of force as F is equal to AY upon L into X. And of course, since the force is a restoring force, we can write it with a negative sign. Again, taking F equal to ma, we get the value of acceleration as equal to minus of a into y upon mass into length into x. Now compare this with the SHM equation. A is equal to minus omega square into x is the equation for SHM. We get the value of angular frequency for oscillation of this wire equal to under root a y upon m into L. Now compare this with the fact that for a spring mass system, omega is given by under root k by m. So whatever is in the numerator of the mass in the angular frequency term, a y upon L in this case, can be thought of as an equivalent spring constant. We can write an equivalent spelling mistake, spring constant, such that K equivalent is equal to AY upon L over here. So we can say that the wire behaves like a spring of constant AY upon L. This will be much easier for us because now we can consider our system to be made up of two springs, one of force constant K equivalent and one of force constant K. And we know that a series combination of two springs gives us an effective spring constant as K1 into K upon K1 plus K. So this effective spring constant K effective will be equal to K equivalent into K. So A into Y upon L into K upon the sum of them, A into Y upon L plus K. We can take L to the numerator and then cancel. So we get A into Y into K upon AY plus K into L. This will be the effective spring constant, and the time period will be equal to 2 pi root m by k. So 2 pi under root m upon k effective will be the time period of oscillation of this block if we displace it with some displacement x, which is of course, if we multiply m over here, matches with option D once again. So again, you have to work smart, not hard, to solve IIT level questions because you don't have time to go through all the lengthy calculations. This is the bare minimum calculation that you will be able to do in the exam within 2 minutes. Otherwise, you will spend unnecessarily a lot of time on this question to take x1, then x2, and then time period t1, then t2, and then add them both. Let's take a look at the next question. We have the fact that water through a pipe which has a constriction has some bubbles moving through it, narrow region. Let's say the cross section area of this region is A2 and cross section area of the rest of the wire is A1. Clearly A2 is greater than A1, and let's say the velocity V1 and V2 exists in both these regions. We need to see whether or not bubbles traveling through the narrow region are faster or slower or bigger or smaller. We know only two equations from fluid mechanics, equation of continuity. Let's apply. A1 into V1 should be equal to A2 into V2. Since A2 is less than A1, so V2 will be greater than V1. A1 is clearly less than A2, greater than A2, sorry. So V2 will be greater than V1. So bubbles in this narrow region will be faster, traveling at a greater speed, and hence option C and D are immediately eliminated. But we still don't know whether bubbles will be smaller or larger. Intuitively, you can say that, okay, since the pipe is narrower, then the bubbles will be pushed inwards and hence they might decrease in size, and you will be tempted to answer option A. But let's see where the maths takes us. We only know one other equation in fluid dynamics, that is the Bernoulli's equation. P1 plus rho gh will be at the same horizontal level, so we can ignore rho gh. Kinetic energy half into rho into V1 square should be equal to pressure at the second point plus half into rho into V2 square. Since we know that V1 square is less than V2 square, pressure at the second part should be less than pressure at the first part. So P2 should be less than P1. If V2 is greater than V1, we know that P2 should be less than P1. Mathematically, we have this now. And we also know that for a liquid bubbles, greater pressure from the outside means a smaller size. So smaller pressure from the inside, so from the outside, means that the bubble will be larger. We also know that the change in pressure outside to inside should be twice of surface tension upon a radius of bubbles. So if the external pressure is greater in region 1, that means it is allowing for a smaller bubble. Greater pressure from the outside, which means pressure difference will be lower, hence radius will be higher. And if the pressure outside is lower, the pressure difference will be increased and hence radius will also increase. So the bubbles will be larger than rest of the pipe. Option B is correct. Again, your intuition might be wrong, you might make some mistakes in the intuition, but as long as you don't mistake any equations, the maths will never lie to you. Maths will always give you the correct answer. Let's do the next question. We have an asteroid orbiting on the planet, explodes into two pieces. Let's say the asteroid was of mass 5m, moving at some speed u towards the left, and it explodes into two masses, one of mass 4m and one of mass m. We know that mass of m has in the same orbit as the previous, so it will also be moving with the same speed u. And we also know that if the radius of the orbit is r, then the orbital velocity u should be equal to under root gm over r. We know this much. And conserving momentum of the asteroid, now the initial momentum was 5 times m into u, and let's say the mass 4m moves with some speed v towards the left, so its momentum will be 4m into u minus of m into u, 4m into v. This will be how the momentum will be conserved now. And taking m to the other side, we get value of v to be 3. V value is 3 by 4 into u, that is 3 by 4 into under root of g into m over r. 3 by 4 Allah, 3 by 2. 3 by 2 gm upon r is the value of the speed of 4m block after the explosion happens. Now we know that for any planet, the escape velocity v escape, or for any orbit of radius r for the matter, any orbit of radius r, if we want to escape from that orbit towards infinity, we need an energy of, a velocity of twice of g into m upon the orbital radius r. If we have this much velocity, then we will exactly be able to escape the gravitational pull of the planet. And the velocity of the asteroid remnant 4m, we can write it as under root 3 by 2 taking inside the square root 9 gm upon 4r, which is greater than 8 gm by 4r, because 8 gm by 4r will be twice of gm by r. So we know that the velocity of the 4m fragment is greater than the escape velocity. since it is greater than escape velocity, it will now escape from the gravitational field. Again, in questions like this, you might be tempted to intuitively say that, okay, since mass small m moves towards the left, mass 4m should move towards the right with a greater speed to balance the momentum, in which case, since the speed is greater, the radius should have to be lower. So it will be orbiting with a smaller radius. You will be tempted to answer option C. But again, don't forget maths. The maths might lead you elsewhere, just like the math led us now to the fact that it will escape the gravitational field of the Earth. Let's take a look at the next question. We have two planets A and B orbiting in radii r and 4r respectively, and we need to determine whether in a quarter year of planet B, how many revolutions will planet A complete. Now we know that according to Kepler's law of orbits, time period is proportional to a radius of orbit raised to 3 by 2. This is Kepler's second law of planetary motion, also known as law of orbits. And from this, we can write the ratio of time periods of planet B and planet A as simply a radius of B upon a radius of A raised to 3 by 2. And we know a radius of B is 4 times the radius of A. So this ratio will be 4 raised to 3 by 2. 4 square root is 2, 2 raised to 3 is 8. So this will be the ratio of their orbits is 8. Now since we can write the period of planet B is equal to 8 times period of planet A, and hence we can write T by 4, TB by 4, which is a quarter year on planet B, will be equal to twice of TA, just multiplying 1 upon 4 on both sides. We get that as planet B completes 1 quarter of a year, planet A will have completed 2 revolutions. Again, as long as you know Kepler's law of planetary motion, rest is just logical application of it to the required system. Now in this question, we have a planet of mass m in circular motion such that we describe a vector A as the cross product of velocity and angular momentum. Let's say this is the orbit of the planet. Approximately, let's say this is the orbit. Okay, let me not even complete it. Yeah, this is the orbit of planet. We know for any point this, the velocity will be in the tangential direction v, the radius will be perpendicular to velocity, of course in the radial direction r, and angular momentum L is equal to r cross momentum mv, which we can write as simply m into r cross v. So from right hand rule, the direction of L will be r cross v. So L will be in my thumb direction, which is exactly outwards from the plane of this board. This is the direction of the L vector outwards, the plane of the board. Now if we define the vector A to be equal to V cross L, so it will be, we can take mass outside into V cross product with R cross V. It's the triple product of V, R and V itself. We know direction of L is outside and direction of V is along the tangent. So V cross L, we will get the fact that the direction of A will be along R. So direction of A will be the same as direction of the R vector. Option D is correct in this case. Again, you could have checked other options one by one also. It will obviously not be a zero vector because V and L are perpendicular. So the cross product will not be a zero vector. Magnitude also you can check by simply multiplying all the quantities. We know it will not be perpendicular plane of orbit because angular momentum is perpendicular plane of orbit, and a cross product involving angular momentum will be perpendicular to the angular momentum. So we knew that the vector would be somewhere inside the plane of the orbit itself, and by right hand rule we saw that it is exactly in the direction of the radial vector. Let's look at the next question. We have neutral gas molecules at some mass and temperature T. We need to see how the de Broglie wavelength depends on the temperature T. Now we know that de Broglie wavelength is defined as h upon momentum p. if we want to relate the momentum with the energy, we can write energy, kinetic energy, as half into m into v square for some molecule, multiplying and divide by m, we get m into v the whole square upon twice of m, and that gives us the famous relation E is equal to p square upon 2m. Now writing P in terms of energy, we get P is equal to under root twice of mass into kinetic energy E. Substituting in the value of de Broglie wavelength, we get the relation H equal upon under root 2 into m into kinetic energy. Now since we know that for an ideal gas, the average kinetic energy E average is equal to 3 by 2 Boltzmann constant into temperature. That is, it is proportional to temperature, which is also one of the postulates of kinetic theory of gases, that at steady state, average kinetic energy is proportional to temperature. And since de Broglie wavelength is proportional to 1 upon root of energy, the average de Broglie wavelength will be proportional to 1 upon average energy, that is 1 upon square root of temperature. Option C will be matching in this case. Let's take a look at the next question now. We know we've been given that temperature of a thin uniform disk, if it is raised by 10 degrees, we need to calculate the percentage of the increase of moment of inertia. We know moment of inertia for a disk is m into r square by 2. So moment of inertia will be proportional to radius square, and using the theory of errors and uncertainty, we get the percentage increase in moment of inertia to be equal to twice of percentage increase in the radius, and we can calculate this as twice into change in r is simply radius into coefficient of linear expansion into delta t upon the radius will get cancelled from the denominator. So we'll get the percentage increase as 2 into value of alpha we've been given as 11 into 10 power minus 16 into temperature rise is 10. This is the value of percentage increase you are getting. It will come out to be 0.22, sorry, not minus 16, minus 6. Again, very simple, just application of 2 or more concepts with some simple remembering will get you the answer very easily. Now in this question, we've been given a PV diagram of a thermodynamic cycle, and we need to convert it into a VT diagram. Now we know that 4 and 3 and 1 and 2 are isobaric process. The VT diagrams for isobaric processes are as follows. They are straight lines such that this is V and this is T. Then pressure at this point P2 will be greater than pressure at this point P1. This is how isobaric processes are represented on VT diagrams. So process 1, 2 and 3, 4 should be straight lines along the origin. So option A and B are immediately disqualified. Now we know that 2, 3 and 4, 1 are adiabatic process, and the equation for adiabatic process is that T into V raised to gamma minus 1 should be a constant, let's call it K. Now this can obviously not be a straight line unless the value of gamma is exactly equal to 2, which for an ideal gas it will not be. So option 4 is also disqualified. The only other option remaining is option 3. So by Sherlock Holmes method, this has to be the correct answer. Let's look at the next question quickly. We have two spherical black bodies A and B emitting radiations at the same rate. So initially the rate of radiation E into sigma into area, which is 4 pi r square, into temperature to the power 4 of A should be equal to E into sigma into 4 pi r B square into temperature of B to the power 4. Initially their rate of radiation is the same. Now if we increase the radius of B to double, RB now becomes twice of RB, and the maximum intensity wavelength of A is halved. According to Wien's law, the maximum displacement is given by some constant B upon the temperature of the black body. So if lambda is doubled, then temperature lambda is halved, then temperature of A has to be doubled. So temperature of A will now be twice of temperature of A. This will be how we modify the system. Now if we calculate the ratio of their energy radiations, then radiation pressure by A or B, right? A upon B will be equal to E into sigma into 4 pi R A the square into twice of TA raised to power 4. And since the radius of B has been doubled, we can write the surface area as E into sigma into 4 pi twice of RB square into TB to the power 4. We know that initially their rates were equal, so we can cancel E sigma 4 pi RA square cancel with RB square, TB to the power 4 cancel with TA to the power 4. Initial rates are equal. We can now apply that fact. So the ratio of their radiation rates will be equal to 2 raised to 4 upon 2 raised to 2, which is simply 2 raised to 2, that is 4. So the ratio will be option C, 4. Again, if you only know Stephen Boltzmann's law and Wien's displacement law, there is literally nothing else in the chapter radiation. That is all you need to know. Next question, we have the fact that water flows into a large tank at some constant rate and there is a hole of 1 centimeter square at the bottom. If we draw the tank like this, we know water is flowing in at a rate of 10 power minus 4. The level of the water, if it remains constant, then if we have a hole at the bottom, we know that water will also leak out with velocity of efflux to be under root of 2g. Water will leak out of the hole at the bottom. Now, in order for level of water to be constant, the rate of influx should be equal to the rate of efflux. We know the rate of influx is 10 power minus 4 and rate of efflux should be equal to area of the hole into velocity of efflux. Area of the hole is 1 centimeter square, that is 10 power minus 4 meter square, into velocity of efflux is under root 2 gh. Rate will get cancelled with area of the hole and the height h should be equal to 1 upon 2g, that is 1 upon 20 meters, that is equal to 5 centimeters will be the answer. Again, very easy question. If you know the velocity of efflux, then just simple application of logic will lead you to the answer very quickly. Now in this question we have that a simple pendulum has time period t1 on the earth's surface, and if we take it at a height of r above the earth's surface, then the time period becomes t2. Now we know the acceleration due to gravity at a height h of the surface, g drops at a height h, and we also know exactly how the acceleration due to gravity drops. Acceleration at a height h will be equal to acceleration at a surface into 1 plus h by r raised to minus 2. And the acceleration at a height equal to radius will be equal to g into 1 plus 1, that is 2 raised to minus 2. That's equal to g upon 4. And we know that for a pendulum, time period is proportional to 1 upon effective acceleration due to gravity. T1 we have normal acceleration g and T2 we have acceleration g by 4. So ratio T2 upon T1 will simply be equal to g upon g by 4, that is equal to 2 will be the answer. D option matches in this case. Again, very easy question. Simple if you know the concept of variation of acceleration due to gravity above the Earth's surface. This is a very easy calculation. Now in this question we have a point particle of mass m inside a potential well, which is k into mod x. Now this is obviously not a simple harmonic motion, because for an SHM the potential energy should be half kx square. If it is related as x square, then this is a simple harmonic oscillation. But since the potential energy is mod x variation, then it will not be simple harmonic, but it will be some oscillatory motion nonetheless. So let us draw in one dimension the oscillation of this particle from amplitudes x naught to amplitude minus x naught, and mean position will be at the center O. Now, the time period will be the time taken for the object to leave the amplitude, reach the other amplitude, and then return back. So, in order to go from the amplitude to mean position, it should take a time of t by 4, where t is the time period, because it is executing 1/4 of its oscillatory motion till the mean position. But since velocity is also continuously changing inside oscillation, we will have to look at the problem continuously. Let us assume that the object goes from amplitude to some arbitrary point at a distance of x, and we need time taken to reach x, which also we can easily calculate by conserving energy. Initial potential energy was k into x naught. We can ignore mod because x naught is positive. And finally, the object will have some kinetic energy half mv square plus some potential energy k into x. Now, if we write down the expression for its velocity, we can write velocity as dx by dt, and we can write down as 2k by m into x naught minus x. 2k by m into x naught minus x, of course with a square root sign. Integrating this expression, we will get how much time the particle takes to cover a distance of x. Let's see, dx upon root x minus x naught, we can write dx over root of x naught minus x, and 2k by m we can keep constant on the RHS, multiply it with dt. Now, integrating from the limits 0 to time period by 4, we can integrate x from x naught, which is the initial position, to 0, which is the final position. And this integral comes out to be minus of 2 under root x naught minus of x. And on the RHS, the integral comes out to be under root 2k over m into simply t by 4. Now, putting limits from x naught to 0, the upper limit is 0, so it will be minus of 2 into x naught minus of course, yes, and initial limit is x naught, so it will be 0. So, putting limits, we get the answer as, so it was minus sign. Putting limits, we get 2 under root x naught as the answer, which will equal to under root 2k by m t by 4. We take 4 to the other side, we will get 8, and bringing 8 inside the square root, we get 64. So from here we get the value of t as 64 x naught into m upon twice of k, that is 32 into m x naught upon k. 32 into m into x naught over k is the time period of oscillation. Option D again matches over here. Again, the calculation is not at all complicated, it's just one simple integral you have to do, but the logic is very heavy in this question. If you get lost in the concept and assume that this will be a simple harmonic motion and the velocity is a into omega, time period is 2 pi by omega, somehow you will calculate a wrong option will be given and you will tick that and gain negative marks. Don't do that. Keep in mind that SHM potential is half k x square, not mod of x. In the next question, we have a string obeying Hooke's law such that if we extend it with x, the speed of sound in the string is v. We know since it obeys Hooke's law, first the velocity of waves in the string will be under root of tension upon mass per unit length v. No matter how much we strain the string, the mass per unit length will not change for small strain since it obeys Hooke's law. And Hooke's law we can write Young's modulus of y is equal to tension into length upon a into extension. x. From here we can get the fact that T, tension, is proportional to extension in the string x, and since tension is equal to extension, velocity will be proportional to root of extension. Velocity will be proportional to square root of extension in the string. Since we know that extension is x for velocity v, we can write the ratio of velocity v dash upon v as square root of 1.5x upon x will get cancelled, and the ratio will be square root of 1.5. Again, using a calculator, you can solve for this square root 1.5. This will be 3 by 2. So root 3 is 1.732. Root 2 is 1.414. It will approximately be 1.22. 1.22 into velocity will be your answer. Very, very simple. If you know two concepts, velocity of wave in a string and Young's modulus according to Hooke's law, you will easily be able to solve this question quickly. Next question, we have a police car moving towards a motorcyclist. This is a police car is moving towards a motorcyclist. Let me go a little farther. And both of them are moving towards some siren. S. Siren emits some sound towards the motorcyclist. Police car also emits some sound towards the motorcyclist. Police car is moving with velocity 22 meter per second and motorcyclist is moving with some velocity, let's say u. Siren is at rest that emits a frequency of 165 and police car emits a frequency of 176, right? 176, yeah. Now, according to Doppler effect, the frequency of the police horn heard will be equal to original frequency 176. And if you are having trouble writing expressions for Doppler effect, remember only two concepts. If a source is moving towards the observer, the velocity in the denominator will be negative, and if a director is moving towards the observer, velocity will be negative for it again. Now, since the detector is moving away from the source, its speed will try to decrease the frequency. So, speed of sound 330 in air minus of u in the numerator. Police car is moving towards the detector, so it will try to increase its frequency and its speed 330 minus of 22 once again. Similarly, the frequency of siren heard will be equal to 165, its original speed, upon the detector is moving towards the source, it will try to increase the frequency now. So 330 plus u will be the numerator and the source is silent. So 330, just the speed of light, will remain. 165 cancels with 330 and we get 2. Now, in order for there to be no beat frequency, both of these frequencies heard should be equal. Equating both of these frequencies, we get 176 upon 330 minus 22 is 308. So 176 upon 308 into 330 minus u should be equal to half of 330 plus u. Half of 330 plus u. Now this again you will have to solve using a calculator. If you can take 2 to the other side, 2 cancels and gives you 154. 176 upon 154, if you calculate quickly, let me remove my calculator and calculate 176 upon 154. 176 divided by 154 gives us 1.143. 1.143 into 330 will be 377. So we can take 1.14 to the other side. We'll get 2.28. U will be equal to 377 minus of 330, which is 47.1 divided by 2.2 approximately, will give us almost 22 meter per second. So value of u is approximately 22 meter per second. Option B is again matching in this case, the same as the police in fact. So since the police and the motorcyclists are moving the same speed, there is no relative motion between them. So technically the police frequency will remain constant and the siren frequency should increase to match it. Next question, we have an electron of mass me given to us accelerating under electric field. It should be have traveling equal distances in time t1 as a proton in the same electric field. Now we know that acceleration on charged particle is equal to the charge into electric field is the force upon its mass, gives us the acceleration, and in this acceleration the distance moved from rest will be equal to half a into t square, that is q into e upon twice of m into t square is the distance moved under a uniform electric field. Now, for a proton, the time taken is t1. For electron, time taken is t2. Or wait, it was the other way around. Yes. So for proton and electron, we can equate the distances and say that q, that is charge on electron proton, is e upon mass of proton is mp into twice of mp into t2 square should be equal to charge electric field upon twice of mass of electron into T1 square. So the ratio of T1 upon T2 or T2 upon T1 we easily get equal to square root of mass of proton upon mass of electron. This is the ratio T2 upon T1 that we require, matching with option B. That's it. That is literally it. T2 upon T1. Yeah, that's them. Next question. We have a neutral conducting sphere and a positive charge placed outside. We have a neutral conducting solid sphere. It is not a spherical shell. It's a solid sphere such that there is a mass of, charge of positive q placed on the outside. Now we know that electric field inside a conductor should be equal to 0 everywhere. There should be no electric field inside a conductor. So electric field due to the charge plus q should be balanced because of the negative charge induced on the surface of the conductor. Since we know that the electric field at this point will be greater and electric field at this point will be lesser due to the positive charge q, then the charge on the surface negative should be non-uniform such that the different electric field values at different points are exactly balanced. So charge will be non-uniformly distributed. Again, it's a very simple logical question, but again, if you make even the slight mistake in your judgment, then you will get negative marks. Remember the basic concept always, that electric field has to be 0 inside a conductor. If you have a high electric field at some point, then charge distribution should be high around that point, and around the other point the charge distribution should be low, such that the electric field is exactly balanced. Now let's take a look at another question. Now similarly, on charge distribution we have a bigger question. In fact, we have a conducting sphere with a cavity inside it and a charge q placed near it. So we need to sketch the electric field lines on it. We know that as we have a charge q over here, there will be some negative charge induced inside the inner surface of the sphere, we know. So electric field line starting from positive should end up towards the negative side. This much is great. But this negative charge should be balanced by some positive charge on the cavity also. Because the cavity is not conducting, there can be some electric field inside the cavity. So balancing positive charge and also a balancing negative charge will be induced over here. And for the entire sphere to remain electrically neutral, there will also be some positive charge induced on the outer surface. So this is how charge induction takes place inside a sphere with some cavity. We know that electric field lines start from positive charges and end towards negative charges. But since there is a charge outside the cavity also, there will be some electric field lines in the cavity as well. So option B is correct. Option D can immediately be eliminated because there cannot be electric field inside a conductor. And option D, sorry, is also incorrect because due to charge distribution, if we only have negative charge over here, there has to be other charges elsewhere that can create more electric field. So option B is correct in this case. In this question, we have a ring of radius r, uniform charge density lambda. If you remember the result for the ring at a height of h with a radius of r, if you remember the result, then you can easily write down the value of force. If you don't, then you will have to sit and derive in the exam 1 upon 4 pi epsilon lambda into 2 pi r, which is the total charge of the ring, into the height h upon r square plus h square raised to 3 by 2 is the force on any test charge kept at a height h at the axis of a ring. Now, you have to check all the options one by one. It will be a simple harmonic motion only if we can neglect h. It will be proportional to h only for small values of h. Only for small values of h will we be able to neglect the denominator h, and hence it will be an SHM. Since we are releasing from a height h greater than twice of the radius of the ring, twice of r, there is no way in which it is an SHM. So option A is eliminated. And the magnitude of force first increases then decreases. That is true. When h is much greater, the value of h is decreasing. Since the denominator has a power 3 and numerator has power 1, as h decreases, the denominator decreases much faster than the numerator. So as a whole, the force increases. When we neglect h for small values of h, the denominator does not change much, but numerator has h multiplied. So as h decreases, the force will decrease for small values of h. So option B is correct. Again, this is an old nest question, so multiple options can be correct. Let's check whether the magnitude of force on test charge near center of the ring, which means for small h, decreases with the radius of the ring. When h value is small, we can neglect h with respect to r. Denominator will be r cube, numerator will be r square, cancels, and 1 upon r square will be the value of force. If r increases, then the force will obviously decrease with increase in r. So option C is also correct. Now to calculate the speed of the particle as it reaches center of the ring, we need to use work energy theorem. The change in kinetic energy half mv square of the object should be equal to the work done by the electrostatic force F dot dh. Now if we integrate F with respect to dh, lambda is a constant, it will come out. So v square will actually be proportional to lambda and not v. Option D says velocity will be proportional to lambda, which is incorrect. V square will be proportional to lambda, hence v will be proportional to square root of lambda. Always check maths, at least try to check the maths before picking an option. Let's go to the next question. Here we have a parallel plate capacitor initially filled with dielectric constant 10. So let's say there is a capacitor with some area of plates A, some distance between plates is D, and without dielectric it has a capacitance of C naught. Initially it will have a capacitance of 10 C naught, and after connecting to battery it will gain some charge. If we don't remove the battery and insert a dielectric of 15, then the new capacitance will be 15 C naught. If we don't remove the battery, the charge on the capacitor will increase with increase in capacitance, and we can write the initial energy stored in the capacitor as half into C1 into voltage square, that is C1 is 10 C naught, so by 2 that is 5 into C naught into V square will be the initial energy stored in capacitor. The final energy stored in capacitor will similarly be equal to half into C2 into V square, that's equal to 15 by 2 into C naught into V square. We know the value of C naught into V square is U into I. So 15 by 2 into UI by 5 will be equal to 3 by 2 UI. So the final energy will be 3 by 2 times the initial energy, which is basically 1.5 times the initial energy. The change in energy in this case will be equal to 0.5 UI. So the percentage change in energy delta U upon U will be equal to 0.5 into UI upon UI, which is equal to 0.5. So there will be a 50% increase in the energy stored in the capacitor. Again, very, very easy. If you know the concept of dielectrics, if you know the concept of energy stored in capacitor, and you are able to apply logic correctly, that is changing dielectric without changing battery, then this is also a very, very easy question. Next, if you have two capacitors connected in series and space between one of them is filled with dielectric. Let's say this capacitor is filled with dielectric constant K and connected in series with another capacitor of capacitance C. The capacitance of this is K into C. The equivalent capacitance is given by 1 upon C equivalent is equal to 1 upon K into C plus 1 upon C. That is simply K C plus C into K. So C equivalent will be equal to K into C square upon C into 1 plus K. C square and C will get cancelled from here. Now we know that the final equivalence is 24 microfarads should be equal to K into initial capacitance is 40. So 40 into K upon 1 plus K is the expression. 40 goes with 4 10 times and goes with 4 as 6 times. 40 goes with 8 5 times and 10 times also fine. That doesn't make quite a difference. We can get an equation for K over here that 6 plus 6K should be equal to 10K. We get K 4K equal to 10. So K is equal to 10 by 4, that is 5 by 2 is the value of K, or 2.5 is the dielectric constant, matches with option B. Again, very, very easy, just combination of capacitors you have to do. Next question, we have an infinite ladder of capacitors. Now, the recipe for solving any infinite ladder problems is very, very simple. Look for the unit that keeps repeating. Take one unit outside and divide the entire circuit into that one unit and rest of the circuit. Let's call the entire capacitance to be C equivalent. So the entire infinite ladder will give us a net capacitance of C equivalent. And now we can reduce the entire rest of the circuit also to C equivalent, because since it's an infinite series, the rest of the circuit is exactly the same as the initial circuit. So we can replace this with a equivalent capacitance. So P and Q from here will have one series capacitor, one series capacitor, one series capacitor as such, and a capacitance of C equivalent connected in parallel. This is C equivalent and others are all C. That's it. Now if you simplify this circuit further, in parallel the capacitors get added. So we have one capacitance C, one capacitance of C plus C equivalent, and another capacitor C connected in series with all of them. And the entire circuit, the series part, should solve to C equivalent. Now writing the expression for equivalent capacitance, 1 upon C equivalent should be equal to 1 upon C plus 1 upon C plus 1 upon C plus C equivalent. You will have to solve this equation to get the answer. You can write 1 upon C plus 1 upon C as 2 by C. 2 by C you can write, and then you can use the fact that C equivalent should be equal to series combination of C by 2 and C plus C equivalent. That will bring us C plus C equivalent into C by 2 upon C plus C by 2 plus C equivalent will be the net capacitance. Now, if you simplify this expression, we know that we need a C equivalent square in the denominator by multiplying these two. So we should get a quadratic equation. Let's see what kind of a quadratic equation we get. C equivalent we multiply by 2. So 2 into C equivalent the square. We will also get 3 into C equivalent plus 1 into C equivalent. That will give us twice of C into C equivalent as the middle term, minus of we will get C equivalent square C square, from here only 1, so we'll get minus of C square equal to 0. Again, I used a shortcut to write the quadratic equation, but you will not do this. You will exactly write down all the expressions and simplify this. Now, once again, we need a quadratic expression, minus of 2c plus this positive root b square minus 4ac, 4c square plus 8c square upon 2 to 4, and minus of 2c upon 2 will get minus of c by 2, 4 plus 8, 12, 4 will come out, 2 will get cancelled, so root 3 by 2c minus of c by 2, that is c by 2 into root 3 minus 1 will be the answer. Option D once again matches. Again, this might look like an intimidating question, but if you can simplify the circuit, the question also becomes as easy as solving one quadratic equation. Let's look at the next question. We have a potential difference across wires of resistance R. Power consumption is W. If we write down W initially as V square by R, and if we cut the wire in half, each of the half will have resistance R by 2, and if we connect them in parallel, then the effective resistance will be even further halved. So the net resistance effective will be equal to R by 4 of the wire. Now, taking the ratios of power consumption, W dash upon W, we know W dash is proportional to, so W is equal to V square upon R. So W dash will be equal to V square upon R by 4. That is 4 into V square by R, or 4 times W will be the power consumption. Option D again matches in this case. Very easy if you know how power is consumed in a wire, and the fact that cutting a wire longitudinally will half its resistance, then it is a very easy question. Now, in this circuit, we have a Wheatstone bridge setup, but it is not a Wheatstone bridge because there is no resistor. It is a short wire, and there is another short wire connected this way. The thing to note is that both of these wires are equipotential. Both of them are equipotential points because they are connected by a wire without any resistance. And whenever you have equipotential points, you can bring them both close together. So if you bring the points together, you will get a resistance network like this. You will have one 6 ohm resistor and one shorted resistor, and another 6 ohm resistor and a 6 ohm resistor connected in parallel, 6, 6 and 6. Now, whenever we connect a straight wire across a resistor, this is called a short circuit. And in this case, the entire current flows through the short wire and no current flows through resistor. In this case, we actually disconnect this 6 ohm resistor and not the Wheatstone bridge resistor. In a Wheatstone bridge, we disconnect the bridge resistor. In this case, we disconnect the 6 ohm resistor and bring the short wires at one point. The equivalent resistance of this will be 6 by 2, that is 3 ohms, and connecting in series with another 3 ohms, we will get current is equal to total voltage 10 upon total resistance 6, that's equal to 5 upon 3 ampere, matching with option B in this case. Again, very easy. If you look just carefully on the circuit for 2 seconds, you will easily be able to imagine bringing equipotential points together and shorting the 6 ohm resistor also. Next question, we have a current of 10 existing in a copper wire. We have not been given the density of charge carriers, but we have been given mass density of copper. We can write the mass density of copper as mass upon the total volume. We can write mass now as the number of atoms, or we need the number of moles. So number of moles n into the molar mass, number of moles into molar mass, we can write as the mass, and dividing by volume we get the density. So mass upon density we can write in terms of molar mass and number of moles, and number of moles also we can write in terms of number of atoms upon the Avogadro's number Na. So mass density becomes something like this: the number of atoms into molar mass upon Avogadro's number into volume. We get number of atoms upon volume as the number density n of charge carriers, and this we can equate to rho into Avogadro's number upon molar weight, rho into Na upon molar weight m. We know density is 9000 given to us. Avogadro's number is 6 into 10 power minus 23, and the molecular weight of copper is 63.5 grams, converting to kgs, 10 power minus 3 we can write. Now we know the expression for current also. Current is equal to number of charge density carriers into charge on each carrier into drift speed into the area of cross section. So we can write the drift speed in terms of the current as simply current, which is just 1 ampere. So we can just write it 1 anyway, into number density into charge upon area, into charge upon cross section area. We can write the velocity of electrons. Now we know 1 upon n, the exact value is this. If we multiply the charge and electron in the denominator, we will get this as 9000 or 9. Oh no, numerator will come forward, 6.63.5 into 10 power minus 3 into okay, nothing. In the denominator we can write now 9 in 10 power 3 into 6 10 power minus 23. Charge on electron is 1.6 into 10 power minus 19, and area is 1 millimeter square. So converting to meter square, we get 10 power minus 3 into minus 3 minus 6 meter square, and we can send minus 6 to the numerator. It will become 10 power 6. This is how the drift velocity will be. 10 power 3, 10 power minus 3 will cancel 10 power 6. 10 power minus 23 cancel to 19. So 10 power 4 will go into the numerator. 1.6 into 6 into 9, we can cancel with 63.5. What will be left? We will again once have to use the calculator for this. Calculator is provided to you. Let me quickly whip out my calculator and let's see what the answer is. 63.5 divided by 9, again divide by 6, again divide by 1.6. 0.74 is what we are getting. 0.74 into 10 power a number of decimal places. So 74 millimeters. Yes, 0.074 millimeters will be the answer. You will have to take care of the power of 10 over here. Using calculator, you can easily do this. Very, very easy question. As long as you can logically relate density to the charge carrier density, this is the most important part. Relating density to carrier density is the most important part. Current is something you have to remember from the current electricity chapter. Next question, we have a uniform magnetic field and a charge is projected at an angle theta from the horizontal with a speed u. Now we can break the speed down into parallel component v parallel to the magnetic field, and perpendicular component V perpendicular. The force acting on the electron will be given by E. No, charge is Q. So Q into initial velocity U cross B will be the initial force acting on the electron. Right hand rule, U is in the diagonal direction, magnetic field is in this direction. So according to right hand rule, the force acting will be inwards into the plane of the paper. When force is inside the plane of the paper, magnitude of the force can be anything. Magnitude can be anything, that doesn't matter, but inward force and velocity perpendicular component is upwards, and there is some parallel component of velocity like this, we know that the charge will move in a vertical circle and the parallel component will pull the charge forward. So the motion is a helical motion. The motion will be helical. And you have to ensure that now the horizontal distance L moved should be such that the object completes one helical motion cycle as it reaches the point P. Now we know the cyclotron frequency for a perpendicular motion because of the magnetic field will be given as cyclotron frequency is Q into B upon M. Again, if you remember this result, it will be easy. Otherwise, it just takes 2 seconds to derive this formula. You will have to derive it in the exam. Better yet, you remember the value for cyclotron frequency, and hence the time period for revolution of cyclotron will simply be 2 pi by omega, that is 2 pi into M upon Q into B is the cyclotron period. Now in this one time period, the object has to move a horizontal distance of L. So U cos theta or V parallel into T should be equal to L. That is, the condition becomes L will be equal to U cos theta into 2 pi M upon Q into B, such that the value of magnetic field B will be equal to 2 pi M into U cos theta by Q into L. 2 pi M into U cos theta upon Q into L. That's it. Option C once again matches now. Don't make the mistake of thinking that the object will move in a circle like this and the diameter of the circle should be equal to the length horizontal it will travel. No. Basic concept is that force is given by right hand rule U cross B. Keep in mind in which direction the force will be. The force F or the centripetal force is in the inward direction. If it is perpendicular velocity, the object will move in a vertical circle and it will be pushed forward by the horizontal velocity. Next question, we have an electromagnetic wave traveling in this direction, let's say direction of travel X, and it is oscillating in this direction is E. All you need to know, don't get confused with the question, three-dimensional vectors, no worries at all. All you have to keep in mind is the direction of polarization should be perpendicular to direction of propagation, E perpendicular to X. If you just take the dot product of both of them, 5 I cap plus B j cap plus 2 k cap dot product with minus 2 I cap plus 3 j cap minus of k cap, this dot product will be 5 into minus 2 is minus 10, b into 3 is 3b, is minus 2 should be equal to 0. Hence b is equal 3b should be equal to 12 and you will get b is equal to 4. Option B will match in this case. Very basic concept. Electromagnetic waves oscillate perpendicular to the direction of propagation. Now this is a question in which you have to know the concept of Lenz's law very properly. Lenz's law states that for any EMF induced, the induced EMF opposes its cause, whatever causes the induced EMF, it will always oppose it. If the induced EMF is caused by a magnet with north pole facing towards the ring, falling downwards, the EMF will be such that it will exert a resistive force upwards. It will be a resistive force, and hence it will take a longer time to fall downwards. Similarly, even if a south pole is facing towards the loop, EMF will be induced such that another resistive force, because it opposes the cause, will be produced. Same resistive force will act on both the objects A and B, and since there is a no magnetic properties of bar C, there will be no resistive force on C. So C will fall the fastest, C will have the least time of falling, and A and B will now have equal time of falling because resistive forces are equal. As long as you know Lenz's law, this question should be very intuitive, very logical for you. Don't make a mistake of thinking that since south pole is facing downwards, it will get attracted towards it. No, both of them will have a resistive force. Next question, we have two metallic spheres such that they are heated to same temperature and mass of S1 is 3 times mass of S2. Since they have the same density, then we can compare their masses by saying that density into 4 by 3 pi into radius of 1 cube should be equal to density into 3 times density into 4 by 3 pi into a radius of 2 cube. So from here, rho into 4 by 3 pi gets cancelled, rho into 4 by 3 pi gets cancelled. We get R1 to be equal to cube root of 3 times R2. So we have a relation in their radii. Now we need to calculate the ratio of their rate of cooling. Remember, rate of cooling, not rate of radiation. Rate of cooling is the rate of change of temperature. In time dt, we know that they will radiate a heat of E into sigma into surface area is 4 pi r square into T power 4 dt time dt. And in this heat, they will lose a temperature according to mass into specific heat into change in temperature delta T. So from here we can write the rate of cooling, rate of change of temperature to be equal to, let us see, E into sigma into A T power 4 upon M into C. So E sigma into 4 pi r square upon mass into specific heat. That means it will be proportional to r square upon its mass. So if we need the ratio of their radii or rate of cooling of 1 upon rate of cooling of 2 will be equal to the ratio of their radii r1 r2 square into the ratio of their masses m2 upon m1. Now we know that the ratio r1 upon r2 is equal to 3 raised to 1 by 3, and the ratio of their masses m2 upon m1 is equal to 1 by 3, since mass of m1 is 3 times the mass of m2. So the ratio of the rates of cooling will be r1 upon r2 square is 3 raised to 2 by 3 upon 3 raised to 1. That is 3 raised to 3 by 3 in the denominator. So we will have a final expression of 3 raised to minus 1 by 3 or 1 upon 3 raised to 1 upon 3. Option D is matching over here. Again, as long as you can apply logically what it means for two objects of same material to have different masses, different radii, and the fact that rate of cooling is rate of change of temperature, not the rate of radiation of heat, this question should be very doable. Next question, we have the two plane mirrors inclined at some angle such that let theta be the angle between them, and after reflection from the second surface, if a light is incident on the first mirror, it retraces its path. So after reflection, it should fall on the bottom mirror perpendicular to it. Only then will it get reflected back again. And from the law of reflection, drawing a normal over here, this angle given to us 30 degrees should also be equal to this angle 30 degrees. And since this is perpendicular, the inside angle should also be perpendicular. This is a normal to the mirror, so this angle should be 60 degrees complementary to it. So if this angle is theta, then for this triangle we have theta plus 60 degrees plus 90 degrees should be all equal to 180 degrees angle sum property. Hence we have theta is equal to 90 minus 60, 30 degrees. From here angle will be A. Plane mirror questions are very, very easy. Basic geometry and basic trigonometry will always lead you to the correct answers. Next question. We have a thin lens of focal length 10 in air. If it's immersed in water, what will happen to the focal length? Remember lens maker's formula, 1 upon focal length in air, which is 10, should be equal to mu of lens 1.5 upon mu of air is simply 1. So mu minus 1 will be the answer. Mu of lens minus 1 into 1 upon r1 minus 1 upon r2. Let r1 and r2 be the radii of curvature. Mu L minus 1 is simply half. So half of 1 upon r1 minus 1 upon r2 we get equal to 1 upon 10. So value of 1 upon r1 minus 1 upon r2 we get as 1 upon 5. Now once the lens is immersed in water, we can again apply lens maker formula as 1 upon f will be equal to mu of lens is 3 by 2 to mu of water is 4 by 3. So denominator will be 3 by 4 minus of 1 into 1 upon r1 minus 1 upon r2. 339 upon 8 minus 1 will be simply 1 upon 8. So it will be 1 upon 8 into this value is 1 upon 5. We know. So this will be 1 upon 40. So focal length will simply be 40 centimeter. Again, if you can apply lens maker formula twice, you will easily get the matching option. Next question. We have a mixture of light in young double slit experiment such that the central maximum of both of the wavelengths coincide. That means for a screen with some, if central maximum of both of them are same, then if we have two fringes of for equal wavelengths, then whenever they coincide with each other, the variation of y distance from the center will be the same. And for a simple double slit setup, we know the path difference is d into y fringe distance upon d, and this should be equal to n into lambda for any wavelength of light. Since the centers coincide, the value of y should be equal when the fringes are coincident. So only n into lambda should be equal for them. For value of 590, we know that the third fringe coincides. So 3 into 590 should be equal to the fourth fringe into unknown wavelength lambda. Value of lambda we get as 3 into 590 upon 4. 4 approximately goes into 590 as 150 approximately. So approximately 450, since the options are quite far apart, 450 is closest to 442. 442 will be the answer. Again, very, very easy question. As long as you can apply logic as provided in the question, you will be able to solve any way optics questions very, very easily. Next question, we have a mirror of height small h kept at a distance 2L away from a building of height h. If we want to stand in the middle of them and see the building image, what should be the height of the mirror? The height of the building is capital H. Let's say the mirror height is some small h. Let me draw mirror height as some small h. It's a pretty small mirror. And let me draw the ground now, flat ground. And if an observer is standing at a midpoint of them, this distance is L and this distance is also L. The height of the mirror is some small h. If we draw a horizontal, This height will be h. So this height will be capital H minus small h. Now rays of light should hit the top of the mirror over here and get reflected back to the observer. According to laws of reflection, angle of incidence theta should be the angle of reflection in this case. And we can see that for this angle, the vertical height is the height of the mirror h. We can equate the value of tan theta from both the triangles. From this triangle, the value of tan theta is capital H minus small h upon distance 2l. This small h upon distance 2l, it should be equal to value of tan theta from this case small h upon l. L and L will get cancelled. All we'll left with is capital H by 2 should be equal to 3 times small h by 2. Hence, we should get the required height of the mirror small l, small h to be equal to 1/3 of the height of the building h by 3. Option C is matching in this case. Again, as I said, plane mirror questions are very easy. Just basic geometry and basic trigonometry will easily lead you to the answer. Next question, we have a mixture of polarized and unpolarized light falling on a Polaroid such that the maximum and minimum ratio of intensities emergent from them is in the ratio 1 upon q given. We need the ratio of intensities of polarized and unpolarized light. Let's say the ratio is equal to R. Let's say the ratio is R. In that case, if we write the polarized light as this polarized light and this is the unpolarized light falling on the Polaroid, the intensity of unpolarized light, let's say it is I. So the intensity of polarized light will be ratio R into I, since we have assumed the value of ratio. The unpolarized light will simply emerge with half the intensity. We know that. And according to Malu's law, the intensity of polarized light should be R into I cos square theta, where theta is the angle between polarization axis and the polarization of the incident light. The maximum value will simply be R into I. So the maximum value of the emergent light, I by 2 will still be there, and I by 2 plus R into I will be the maximum intensity of polarized light. So if we write the maximum value and minimum value like this, maximum value should be R into I and minimum value should be equal to 0. So the ratio of the maximum to minimum, if it is given to be Q, we can write Q as the ratio of max to min intensity, that is simply I by 2 plus R into I upon minimum intensity only to unpolarized light is I by 2. Getting 2 from here to here, we can cancel I and we can cancel 2 from the denominator also, and we get the value of Q to be equal to 1 plus twice of R. Yes, exactly, 1 plus twice of R is all that remains. There is nothing in the denominator. And this should be equal to the value Q. So the value of R will be half into Q minus 1. Yeah, half into Q minus 1 should be the value of R. Again, simple algebra. Option A matches with this. As long as you know Malu's law and the fact that cos square theta has maximum value 1 and minimum value 0, this question is very straightforward. The ratio of max and minimum, if you take correctly, then you will be able to get the correct answer very quickly also. Next question, we have the minimum distance between object and its image through a convex lens. Again, fundamental concept of physics. For any condition of maxima or minima for any system, you will always have symmetry somewhere in your problem. There will be some symmetry either in your system or in some expression. How can there be symmetry over here? Let's say we have some convex lens like this. We can draw its optical axis. Fine, it's a good optical axis. Remember, positive x-axis is always towards the right and origin of the mirror is always here, lens. Now, object and image have to be equidistant for symmetry to take place. Let's assume that the distance between object and image is d, so that distance between object and the mirror lens are d by 2 and d by 2. Again, we conveniently take the distance between both the object and image to be d, so that as and when we get the value of d, we immediately have the answer. We don't need to calculate further. First point of logic, maxima and minima leads to symmetry. That will solve half of our problem, and rest of the problem will be made very easy by taking a convenient choice of variables. We have taken d, so as soon as we solve for d, we have the answer directly. Now, object distance, image distance, since positive x-axis is towards the left, the object distance is negative. So, in the lens formula, 1 upon f is equal to 1 upon v minus 1 upon u, that is 1 upon focal length given to us is 10, should be equal to 1 upon v is d by 2, so 2 by d minus of 2 by d, because object distance is negative. So, we get 10 is equal 1 upon 10 is equal to 4 by d. From here we get, so just 1 upon, let me write properly, 4 by d. Hence we get the value of d to be equal to 40 centimeter. Again, convenient choice of variables as well as a very smart logic will have very easy solution. Next question. We have a light source placed at the bottom of a pool such that we need to calculate area of illumination. Height of a pool is given to us. Let's say height of a pool is given to us as h, and ray of light at an incident angle equal to critical angle of water, theta critical, will cause it to escape through the surface. We need the radius r of the point where it hits the water. In order to relate r with h, what we need is tan theta critical, but what we have is sin theta critical. From Snell's law, we know it is 1 by mu, that is 3 by 4 for water. But if we want the tan value, all we can do is draw a triangle 90 degrees. This is theta critical. Sin theta critical we can write as 3 by 4. So, the hypotenuse will be under root of 4 minus of 9, that will be root of 7 is the value of base. So, tan theta critical is 3 by root 7. Tan theta critical we get simply 3 by root 7. This much trigonometry you should know at this point. So, now we can equate tan theta critical to be equal to radius upon the height h from this triangle and this will be equal to 3 by root 7. We get the value of r square as 9 by 7 into h square, that is 25. From here we get area of illumination is equal to pi r square multiplying by 3.14. Again, you will need a calculator for it. Approximately 25 into 3 by 7, approximately 2, 23, 27, 7, 4 is 28, approximately 100 you will get. Approximately you will get area as 100 meters square. Option A matches over here. As long as you know total internal reflection and some basic trigonometry and geometry, you will easily be able to solve questions like this. Next question we have, at time t equal to 0, container has n naught radioactive atoms. There is some decay happening and there is some addition of nuclei, and at some time we need how many nuclei will be present in the sample. Now, if you just know the law of radiation, radioactivity, that is dN by dt, rate of decay will be equal to minus of lambda into n. Now, since we are adding impurities per second at a constant rate, there will be plus c also. Again, if you just know law of decay, you will be able to modify the law given whatever system in the problem is described. Now, since let us conveniently write n without any coefficient, so we can take minus of 1 upon lambda. On the other side, dn by dt should be equal to n minus lambda by n minus c by lambda, sorry. This is how we will get our differential equation. Integrating this equation, dn upon n minus c by lambda, we can calculate the value of n minus c by lambda will be equal to minus of lambda into dt. Integrating time from some 0 to capital value t, we will get integration from initial value n naught to final value of capital N. Integration will simply be a logarithmic integration, and log of, in the numerator we will get n minus c by lambda, and denominator will get n naught minus c by lambda, and on the RHS we will have minus of lambda into t. Getting rid of the log, we will get e power minus of lambda into t, and taking the denominator on the other side, we get n minus of c by lambda to be equal to n naught into e power minus lambda into t minus c by lambda into e power minus lambda into t. Again, taking c by lambda to the other side, we can take c by lambda common and we'll get 1 minus lambda of delta t. So we get n equal to c by lambda plus everything. So c by lambda you can take common, 1 minus lambda delta t from here we will get, and plus n naught e power minus delta t. Option C will be matching in this case. Very, very easy. Just remember law of reactivity. Literally every problem can be solved simply by this one rule. Next question, we have following reactions. In nuclear reactions, just like we balance chemical reactions in chemistry, in nuclear reactions, all we have to do is balance the number of protons and the total number of neutrons. Let's see. In the first reaction, LHS has 7 plus 2 protons and RHS has 8 plus some number of protons of X. So from here we get X will have 1 proton. And similarly, balancing the total number of nucleons, the LHS has 14 plus 4 nucleons and RHS has 17 plus some nucleons of A. So X, sorry. Balancing again, we get the number of nucleons of X to be equal to 1. Since X has 1 proton and 1 nucleon, which is the proton itself, we know X has to be a proton, it can't be anything else. X nucleus is simply a proton. Similarly, if we balance for the second reaction, the LHS has 4 plus 2 protons, RHS has 6 protons, and number of protons in Y will be 0 hence. And the number of nucleons on the LHS is 9 plus 4. Number of nucleons on the RHS is 12 plus number of nucleons in Y, and hence Y will have only 1 nucleon, 0 protons and 1 nucleon. So the nucleon has to be a neutron, it can't be anything else. So X will be a proton and Y will be a neutron in this case. Very, very easy. Nuclear reactions are very easy problems. The entire modern physics and semiconductors, in fact, very, very easy. In this question, we have electron which is accelerated by constant electric field. We know that the de Broglie wavelength is defined as h upon mass into velocity. For electron accelerated by electric field, its acceleration will be equal to its force upon its mass. Hence, we can write a velocity as simply acceleration into time. Now, if we take velocity in the denominator, mass will get cancelled with m, and we can write the de Broglie wavelength as simply h upon E into electric field, charge electric field into time. We can differentiate this with respect to time, d lambda by dt 1 upon t is differentiated simply as minus of 1 upon t square. So minus h upon electric charge, electric field into t square will be the rate of change of electric field. Similarly, if we differentiate it again, we will get second derivative of lambda de Broglie equivalent will be equal to 1 upon t square just gives minus of 2 upon t cube. So it will be twice of h upon electric charge, electric field into t cube. Very simple differentiation, very simple manipulation of de Broglie equivalent. We will easily get 2h upon e in t cube. D will match the answer. Very simple questions in modern physics. Now we have a logic gates question. It might be asked in IIT since it was asked in NEET also. We have a combination of logic gates. Don't worry about anything else. Boolean logic, again, not important. Inputs X and Y, not important. What is important is that a NAND gate has an output of 0. If you remember the truth table of NAND gate, since it's an inversion of AND gate, when AND gate gives 1, NAND gate will give 0. So both the inputs of NAND gate, if they are 1, only then will the output be 0. So the outputs of XOR gate and the AND gate both have to be 1. XOR gate, known as the exclusive OR gate, will only give a high output 1 if both of the inputs are different. If both of the inputs are same, it will give a 0 output. So if one of them is 1, then other input P has to be 0 for XOR to give a high output. Similarly, AND gate will only give a high output if both of its inputs are 1. If one of them is 1, then Q also has to be equal to 1. So P equals 0, Q equal to 1 will be the answer. Even if you don't know how to write down the complete truth table of everything, just judging by the names of the gate, you should be able to relate when they will return a high value and when they will return a low value, as and how required by the question. Last question, we have binding energy per nucleon of X10 is 8 MeV. So total binding energy of the 10 isotope will be equal to 10 nucleons into 8, that's equal to 80 mega electron volts. And similarly, the binding energy of the 11 isotope will be equal to nucleons 11 into 7.5, that's equal to 82.5 mega electron volts. In order to remove a neutron from X11 will go to X10 plus some neutron. All we need is the difference in binding energy will be the energy required. Difference in binding energy you can clearly see is 2.5. Difference in binding energy will be the energy of reaction, which is simply 2.5 mega electron volts. Option B is the correct option. Again, as long as you know that binding energy difference is the energy of reaction, you will easily be able to solve nuclear physics questions also. So these were 50 very important questions. Keep in mind the different techniques that we used to reduce the amount of time taken and to reduce the calculation load, because you will not have enough time to decorate each and every page, write each and every solution very properly and then take the answer. No. The key is to take as many quick educated shortcuts as you can, use as much logic as you require, and smartly choose how you approach a question such that very simple and very quick calculations will give you the answer. All the best and see you at your dream institute.